Okay, so now a few more things after this. So the first thing is about the critical isotherm. So remember that all isotherms of the van der Waals gas are like this, so non-monotonic, up until the critical temperature, which would be this one here. So this is the critical temperature, and these temperatures down here are less than the critical temperature. So this critical isotherm, you can see that there is some molar volume somewhere. Okay, let's call it molar volume critical, like this, in which the partial derivative of the pressure with respect to volume has an extremum at constant temperature. Okay, so what extremum condition means, the first derivative is equal to 0. And the second derivative is also equal to 0, because what we see here is not a maximum, is not a minimum. What we have here is a saddle point. Okay, so remember, saddle points are points of a curve in which, let me just make some space here, are points of a curve in which the second derivative vanishes. So we have that the first derivative, that's the normal extremum condition, vanishes, and the second derivative also vanishes. So imposing these two things, we are able to find both the critical pressure and the critical volume. Okay, so with these two conditions we can determine the point VC PC, okay, which is this point up here. And because of course we have the equation of state, from the equation of state we can also obtain what the critical temperature is in terms of the parameters of the problem. So in the lecture notes I have worked out what the critical volume, critical pressure and critical temperature are for the van der Waals gas. This is something we're going to do in the synchronous session of week 7. And let me just say here one thing, which is whatever the actual value of critical volume, critical pressure and critical temperature, we can use it to turn the equation of state into something dimensionless. Okay, so we can define a dimensionless, let's say, calligraphic volume like this, which is the molar volume divided by the critical volume. We can define a dimensionless sort of calligraphic pressure, which is the pressure divided by the critical pressure, and the same thing for the temperature. Let's write it like this. So it's actual temperature divided by critical temperature. So in terms of these dimensionless variables, the van der Waals equation of state is what is known as the van der Waals equation of corresponding states, which I'm just going to copy. You have it in the lecture notes. It's like this, like that, and then the volume term looks like this. Well, always remember this is a different thing. It's a calligraphic letter. It's not the actual molar volume. And this equals 8/3 of this calligraphic temperature. Okay. So you see that the substance dependent coefficients A and B have disappeared from this expression, and every van der Waals gas obeys this equation. So imagine that we have two different gases. The two different gases have different critical volume, different critical pressure, and different critical temperature. If, imagine now, these two gases are presumably at different volume, different pressure and different temperature, but the ratio of volume and critical volume, pressure and critical pressure, and temperature and critical pressure is the same for the two gases. Then we say that the two gases are in what's known as corresponding states. Okay, so gases in corresponding states are gases for which this rescaled dimensionless pressure, volume, and temperature have the same values. Okay, and these gases physically behave the same. So that's corresponding states. Fine, that's the notion I wanted to introduce, and this is the van der Waals equation of corresponding states. Okay. Fine. Another remark, now that I have made more isotherms here in this plot, is that I'm just going to draw, roughly the Maxwell line for these isotherms that I have included here. I'm going to make a few more isotherms just to make my point clearer. Something like that. Something like that. Opa. Okay. So imagine that you have, all the isotherms below the critical isotherm, and you calculate, well, what's the point where the Maxwell line cuts the isotherm on the left, so that is when all of the gas becomes liquid as you compress, and you also find the beginning of the Maxwell line on the other side, and you sort of join these things. Okay, so let's just make a different line that joins all of these points. The top will be precisely at the critical pressure and critical volume, and there we go, down like this. Okay, so this whole region that I have now highlighted here with this red curve, so all of the points that fall under these curves are points at which the gas is in the saturated vapor situation. Okay, so here we have coexistence of the gas and the liquid phase at the constant equilibrium temperature. So this is what is going on in this red area here. And to the left of this red area, there's just liquid. Okay, so this is, if you are anywhere here, you are in the liquid phase. Okay, so let me just make this right, like this. Okay, so here, your van der Waals fluid has turned liquid. And if you are to the right of this area here, you are in the gas phase. Okay, so let's just draw this in yellow, for instance. Now, the point I want to make is that it is possible, perfectly possible, to design a process for which you have a gas and you go all the way to the liquid part without ever going to the saturated vapor phase. Okay, so imagine you are sitting in this isotherm here, and instead of compressing at constant temperature, what you do is you heat up your gas. And you heat up your gas until you are above the critical temperature. Okay? And then you follow an isotherm, and this isotherm is going to be monotonic, like, for instance, an ideal gas isotherm, like that. And at some point, when you are at higher pressure that I cannot draw here, you cool down your system until you fall at a temperature, say, under the critical temperature, and you are down here. Okay, so you heat up your system, you compress your system without changing phase because you are above the critical temperature, but then you cool your system down, and you fall to this point, which is in the liquid phase. So you have, in a continuous manner, you have reached the liquid phase from the gas phase. So it's not always necessary to have this coexistence of liquid and gas for a gas to become liquid. Okay, so you can also do it in a continuous manner. And this is actually part of the title of the original paper of van der Waals. When van der Waals introduced his equation, he was studying precisely this situation in which you can interconvert gas and liquid in a continuous manner.